we will be cutting the question and answer session to 30 minutes. That way there's still time for books to be signed and whatnot. But if you have a question, you can simply raise your hand. Alvaz and I will be walking around with a microphone, and we will also periodically be interjecting with questions we have on our Twitter feed with hashtag Greene at Rhodes. Thank you for attending.
Ben is right here. This gentleman.
If space was created during the Big Bang, how can it be infinite?
If space were created at the Big Bang, how could it be infinite? And it's a good question, and it is a question that highlights the failure of some of the visualization that we often use to explain these ideas. Where'd the questioner go? Yes, there he goes. Right, so in all of my visuals, and just about any visual you'll ever see that has to do with the Big Bang, we picture the universe as this little tiny thing. And then you're right to say, how could a little tiny finite thing turn into an infinite thing if we believe that space is today infinite? We don't know that it is infinite, but let's assume that it is to address your question. And the answer to that question is, when we draw this little thing over here, we're not talking about the entirety of the universe. We're talking about the entirety of what today is the observable universe, the part of the universe that we can see. If we were to draw the entirety of the universe at time zero in the Big Bang theory, if space is infinite today, then it would be infinite back then. Infinitely big, with this swelling happening everywhere on this infinite expanse. And you know that from the reason that you asked the question. If it's infinite today, then further back it might be half of infinity, which is infinity. And further back still it might be a tenth of infinity, which is infinity. And no matter how you slice it, as you go further and further back, the density across space would grow higher and higher, but the extent of space would stay infinite. Yes, go ahead. That's right. So if space was created, now again, as you see, I've shown you the state of the art in what we mean scientifically by those ideas, and in nowhere do I answer, or does anybody answer the question, well, why is there something rather than nothing? That's the deepest question of all, and I don't have the answer to that, and thankfully I'm not the only one who says that, otherwise they should in this talk, but nobody on planet Earth knows the answer to that question. But if space was created at the Big Bang, it was created infinitely big. Now, for those who use that language or think of those terms, I have no idea if it's used, if the universe was created by something, well, presumably that entity isn't limited to create something finite, so you shouldn't be confused by that. But scientifically, that's completely unsatisfying, and we ultimately want to come to some mathematical idea that will show us where everything I'm talking about here came from. We can't do that yet, but the hope is that one day we will.
Thank you. We have one question.
Over here. Is it possible to detect one of these other universes?
Is it possible what?
To detect.
Is it possible to detect one of the other universes? Again, a key question, because if there is absolutely, fundamentally no way to ever detect one of these other universes, then what would we be doing here? Then we are just talking a lot of poetic, philosophical words that have no means of ever being verified, no means of ever knowing whether the ideas are right or wrong. So the answer is that in principle there are ways to detect these other universes, and the picture actually suggests what that might be. Imagine you've got two universes out there. Each of them is expanding. If they were spawned sufficiently close to each other, then their rate of expansion will be greater than the rate at which they're pushed apart by this repulsive gravity that's out there, which means that the universes can collide with each other. Now, calculations have been done as to what we would see if our universe had that kind of fender bender with another universe. Now, if the collision is too dramatic, we wouldn't be here to do the calculations, but on a more glancing blow, the implication would be a series of ripple-like patterns in that microwave background radiation. So I showed you these. I don't know if you could have seen it. Maybe you did. So we had these graphs up here with this tremendous agreement between observation and theory there are the possibility of even finer patterns in that microwave background radiation. And if they fell into the predicted pattern arising from universe collision, that would be indirect evidence that the other universes are out there. So in that sense, the answer is yes.
All right, we have a question from our Twitter feed from Hannah Delagi. How many other universes exist that have the perfect amount of dark energy to exist?
Well, in most of the forms that we use to talk about these other universes, the totality of the other universes out there is actually infinite. And that isn't, again, too surprising because the notion of time really applies, time as we know it applies in our universe. When we talk about the whole collection, it's kind of a timeless realm, even though we imagine that each one is being created, like one after the other. But even that language requires some notion of time that applies to the whole thing. So if you take out the temporal quality and just look at the whole thing, then it's as if you're looking over infinite time. And therefore, it isn't too surprising that there'd be infinitely many universes out there. If the fraction that have just the right amount of dark energy is even infinitesimal, well, an infinitesimal fraction of an infinite number still yields an infinite number of universes. So the answer is probably, if these ideas are correct, infinite. Now there's interesting and curious implications of these ideas, right? So if you calculate the number of distinct particle configurations in a given volume of space, it turns out that that's a finite number of distinct particle configurations, which means if there are infinitely many universes out there, there aren't enough distinct particle configurations to go around to make them all different, which means sooner or later the particle configuration starts to repeat. It's sort of like if I have a deck of cards, there are a lot of orders of the cards if you keep shuffling them, but there's a finite number of different orders. So if you shuffle the cards enough times, sooner or later you're going to get the same order of cards. Now for cards, that isn't too dramatic. But for particle configurations, it is. If you have the same configuration of particles out there somewhere, well, what would that mean? Well, it would mean that, I'm a collection of particles in a certain configuration, as are you, and you, the Earth, the Sun. The same configuration of particles would mean this reality would be repeated out there. In fact, it's even easier to get almost duplicates in that sense, right? That's like doing a shuffle of the cards and almost getting the same order. That's even easier than getting exactly the same order. A configuration of particles that's almost but not identical to ours might mean that, I'm standing over there and you're standing over here. Or, more dramatic changes to reality that may look familiar, but things are just not quite the same. In fact, when I first gave a talk on this, since you asked the question, I remember there was one elderly woman in the front row, and she said to me, but if there could be other universes out there where the particle configuration is close to ours but not identical, does that mean there's a universe out there where Sarah Palin is president? I'm not a political person, so I'm not going to enter that conversation. Luckily, a guy in the back raised his hand and said to the woman, didn't you hear what the good professor said? The particle configuration must be compatible with the laws of physics.
Go ahead. The galaxies are expanding away from each other, and yet our closest galaxy, the Andromeda one, is supposed to collide with us. Could you reconcile for that?
Yeah, so again, the key idea in all of these cosmological discussions is that you are looking at the largest scale behavior of the universe. So I can even give you a more dramatic version of the question that you just asked, which is often asked of me, which is, look, if space is expanding, why aren't we expanding? We've got a lot of space inside of us. We're mostly empty space. So why aren't we growing too with this cosmic expansion? And the answer to that question is the same as the answer to your question. We are held together by forces that are stronger on small scales compared to the outward swelling of space. The outward swelling of space is something that gains strength over larger and larger distances. Why? Larger distances means more space, means more dark energy doing the pushing outward. So over the largest of distances, this kind of outward push will always win. But over shorter scales, there's historical contingency, how the galaxies formed, how they were moving when they were formed, the forces that are acting between them and the constituents within them, and those things can overwhelm the outward pushing. But on the largest of scales, they will always lose.
So from my limited research, I came across the idea that Einstein did not believe that space existed objectively, like without matter. He believed that it was a consequence of matter and gravitation and the field associated with it. Does quantum physics or string theory actually speak to that?
You know, we don't really know what the full answer to that question. It's, again, one of those deep ones. It's a somewhat philosophical question because the issue is ultimately, if you have space and somehow remove the sun and the earth and the moon and every other constituent and every atom and every particle, the question has long been asked, what remains? Is it the environment? Is it empty space, or is it nothing? I mean, the analogy that you can think about is, if I have an alphabet, I got 26 letters in the English alphabet, and I start throwing away W and X and A and B. When I throw out the last letter, what's left? Is it an empty alphabet? Most people would say no, because the alphabet comes into existence with the letters that make it up. Similarly, if I throw all this stuff out of space, what's left? Is it empty space, or does space kind of only have meaning when there's stuff inside of it? Now, as you can see, it's a hard idea to test experimentally, right? It's hard to empty out the universe. But you can study that question to some extent mathematically. And one of the results of general relativity, interpreted in one way, not everybody agrees even on what I'm about to say, but one interpretation of general relativity, which I do think agrees with Einstein's, is that he's basically saying you can't ever totally empty out space because space always has the gravitational field. Even if there isn't any curvature, that just means the gravity is of a very specific sort. But mathematically speaking, if you don't mind my segue into that language for a second, the metric tensor would always be there. So if that's the case, gravity is in some sense always there, so no matter what, you can't ever remove it. And in that sense, Einstein says space will always exist, because it's always inhabited by basically gravity.
Hi. If mathematically we can't determine what happens at a time zero for the Big Bang, why do we cling to an idea of a time zero as time that is something that has a beginning instead of something that's infinite in both directions?
So not everybody does. So I should say, the question is, if we don't know what happens at time zero, maybe we shouldn't cling to that as a special moment. And indeed, there are many theories now that have been put forward where time zero isn't that special, where there's a pre-Big Bang era, and there are pre-Big Bang theories that imagine time goes down to minus infinity, and there are mathematical descriptions of what happens there. There are other theories, for instance, the Cyclic Universe, that was proposed by one of the guys over here, Paul Steinhardt and collaborators, which imagines that the universe repeats in time so that there can be time zeros in any cycle, but that isn't the end or the beginning. It's just an interesting moment in an ever oscillating universe. So yes, many people do speculate on other ideas where time zero isn't as special as it was back in these early ideas. We don't know if those theories are correct, but they certainly are studied for much the same reason that you suggest they should be.
Sure. So I have a very rudimentary understanding of this stuff. I'm not a scientist at all, but I understand that in string theory, apparently there has to be like 11, I think, or 10 dimensions for it to make sense mathematically. Could you say a few words so we can sort of grasp this idea of an 11-dimension universe, or what that means?
Oh, yes. Yeah, there's a great story. Mathematician Thurston at Princeton, who was teaching a class on higher dimensional space, a mathematics class, and he's lecturing about 6-dimensional spaces, and he looks out in the class, everybody looks a little bit confused, and he doesn't understand why they're confused, and he kind of walks over to the side of the room and starts to think for a while, and says, I know why you're all confused. It's so much easier to picture this stuff in 12 dimensions, you know. But for the ideas of string theory, so yes, I didn't talk much about string theory, in fact, anything about string theory really, but when you go to the other end of the spectrum, we were talking about the big things for the duration here today. When you try to discuss the small things, the molecules, the atoms, the subatomic particles, a whole interesting collection of ideas emerge, quantum mechanics being the first, and then if you probe more deeply mathematically, you are led, as we have been, to the possibility that the fundamental constituents of matter are little filaments, little string-like filaments that can vibrate in different patterns. And the different vibrational patterns of these little filaments give rise to the different particle species in the world around us. So in these ideas, an electron wouldn't be a little dot the way we ordinarily describe it. It would be a little loop vibrating in one pattern. A quark wouldn't be a little dot. It would be a little filament vibrating in a different pattern. Now, that's the basic idea of string theory. And when you study the math behind that, much as you noted, we find that the math does not work if the universe only has 3 dimensions of space and 1 dimension of time. Now, you might say, well, that's a pretty good clue that you should move on, study something else. And that may be the right answer, but we also find that if you have an open mind and allow for there to exist other dimensions beyond left, right, back, forth, and up, down. In fact, if you allow 7 extra dimensions of space that we don't see, then the math works. Now your question is, what does that mean? And it really means that in addition to being able to walk this way, and this way, if I was small enough, I'd have other choices. And I don't mean like a diagonal, right? I mean, that's like going this way and this way simultaneously. I'm talking about other directions, other dimensions that you'd be able to move that we are not aware of because we're so big and clumsy, according to these ideas. And a good analogy just to keep in mind is, imagine I have a garden hose. This is our canonical analogy. Imagine I have a garden hose, right? On its surface, there are 2 dimensions. Left, right, and then this sort of circular dimension that goes around it. So an ant on the garden hose can walk in any of those 2 directions. But look, if I make that garden hose really skinny and you look at it from far away, you don't see that curled up part of it, you only see the length. So you'd think that the garden hose only has left and right. And you'd be wrong. And you'd prove to yourself you're wrong if you had a powerful magnifying equipment and you realize, whoa, there's another curled up dimension that my eyes missed. Our thought is that may not just be an analogy, that space may have that quality. So left, right, back, forth, up, down, they're like the big part of the hose. We see them. But just like there's a curled up part of the hose that we don't see if it's small enough, there may be curled up dimensions all around us, so tiny that we don't see them, but yet they're there. That's the idea.
All right, we have another Twitter question from Joseph Gross. How many years will it be until that dark universe you described happens?
The dark universe where everything disappears. That will be in 10 to the 12 years. Sorry, I did that calculation 2 weeks ago. 10 to the 12 minus 2 weeks. Sorry.
This question again, or comment again, is about observable universe. Big Bang happened about 13 billion years ago. So since then, currently our observable universe is about 40 billion light years. When the inflation is going to be at the rate of speed of light, we are going to see the darkness, which will be end of our observable universe. So is it fair to say, or how would we interpret that at the time when the inflation started, our observable universe was infinite?
Let's see. So I'll do my best. I may not have caught the question precisely, but in much the way that we discussed earlier, that if space is infinitely big, it has to always be infinitely big, then if that is the correct model for space, then even at the time of inflation, space would have had this infinite extent. Now, when you think about the extent of space, you have to be a little bit careful. So you mentioned that since the universe is about 13 or 14 billion years old, that the extent of space should be about 13 or 14 billion light years. That makes a lot of sense, but it's not actually correct. When you take into account the rate at which space expanded, and it could have expanded and would have expanded faster than the speed of light in the earliest moments of the universe, when you actually take that into account, from one end of the observable universe to the other, it's about 90 or 92 billion light years today, not just 14 billion. But again, that's a finite number. So if you're only concerned with finite versus infinite, then that is sort of a switch. It either is or is not, and it will always be or will always be not. You can't go from one to the other. Let me just finish this answer with one other thing that may be relevant to what you're asking. In all the pictures I showed you, the universes were like these balls, these spheres. And you might say, well, are you then committed to the universe being finite? Because the sphere certainly looks finite. I can put my arms around it, right? It's this finite size. It's a remarkable fact that indeed from the outside, the bird's eye view, each of the universes in this inflationary multiverse would be finite in size as the picture depicted. But if you were to insert yourself into any of these universes, then within them they appear infinitely big in spatial extent. Why is that? It's the wonders of relativity. Space and time to the outside person are not space and time to the inside person. And the way space and time relate to each other is such that infinite time from the outside perspective translates into infinite space on the inside perspective. So those universes, even though they looked finite, are infinite to anybody who is inhabiting them.
All right.
Put that in your pipe and smoke it.
Sorry. Sorry. Okay. We'll be taking this question and then one more question.
Okay, so in this bubble bath of multiverses, do you think that we're still following the quote-unquote rules that we're dealing with in this universe? And do you think that there could be two simultaneous multiverses overlapping, whether that's in time and space or outside of time and space? And then what are we bathing in, I guess?
Well, you're making my head hurt. So yes, the answer to the first question is yes. So anything that we're talking about here, we are imagining that there is a set of mathematical rules that is generating all of the ideas, the conclusions and the conjectures. They're all coming from the mathematical rules, and therefore the mathematics applies to the whole thing. So everything that I've said fits into that context. Could I envision that there's like some kind of parallel universe, you know, a multiverse that is separate from this multiverse? Can I imagine it? Yeah, I got an imagination. I can imagine it. You know, I can also imagine that the moon is made of cheese, right? And the reason why I don't focus on the moon being made of cheese is because there's nothing that I see in the equations that leads me to even have a remote possibility or speculation that the moon is made of cheese. So I'm like, it's possible, I'm just not that interested in that idea. Similarly, when it comes to this other multiverse idea, it sounds cool and, you know, be a good movie or something, but when it comes to science, I see nothing in anything that we're doing that suggests it. And that's why, however interesting or cool it might sound, it doesn't draw me to it in any way. If the math that we develop should lead to that, then yes, we would think about that. We'd think about it intently. Now that was part A and B. What was part C?
What are we bathing in?
What are we bathing in? I mean, I like bath salt. You know, my wife likes L'Occitane. It's expensive, but no. What are we bathing in? if you're talking about the steamy stuff that was surrounding all of the universes, then that is the very same dark energy that I was describing earlier on. And I'm glad you asked the question, because I didn't say it, but it's worth mentioning right now. So we often think about the Big Bang, and my visuals again reinforce this idea, as something expanding outward from a small size. If the multiverse picture is actually true, the right way of thinking about it is a little bit different. The right way of thinking about it is, you've got this big cosmic expanse filled with this dark energy. Think of it like big Turkish steamboat, all filled with steam, and it's all rapidly expanding because of the repulsive gravity. Various locations in that environment, the dark energy decays, which opens up a little hole in this big bath. And it's that little hole that opens up that is universe upon universe upon universe. Each hole is its own universe. So it's not so much as something expanding and exploding outward within this environment. It's more regions that are dropping out of the rapid swelling because the dark energy decays. And it decays into particles that make up stuff like you and me. So that's kind of the difference. The bath is the norm. The universes are the little things that happen when the steam decays.
Thank you. We'll be taking one final question, but stick around. If you have more questions, there will be a book signing immediately afterwards. You can purchase a book if you would like and have him sign it and ask your question then. And feel free to keep tweeting questions out with that hashtag #Greene@Rhodes. And if you would like to answer some of them through the social media, you can, if you would like.
Thank you.
With the discovery of the Higgs boson a few years ago, has that led to any further confirmation or disapproval of multiverse theory, or for supersymmetry, or any of the other theories that are out there?
Yeah, so the quick answer is not really. But you can't overstate how profound that moment was in the history of this kind of science. So when you think about the Higgs idea, it started in 1964. Peter Higgs walking around the outskirts of Glasgow and has this idea and writes it down for how particles will gain mass. And it has to do with a bath of energy filling space. Ooh, sounds familiar, right? And particles going through this, and they're experiencing kind of friction-like force as they try to push through this bath, and that's where their mass comes from. Writes it up into a paper, sends it to the journal rejects it. He rewrites it, changes a little bit, sends it to another journal, it gets published. Nobody takes it seriously. Nobody thinks it's right. He goes on a kind of a crusade, lecturing on it in various places around the world, and little by little, as people studied the math, they were like, wow, this makes a lot of sense. This might actually possibly be right. 1970s, by 1985, I'm a graduate student, and I'm learning about this Higgs idea in my quantum field theory class. And the professor is teaching the idea with such certainty that, as I was mentioning earlier today in our gathering, for many months after that class, I didn't know it was just a theory. I thought it was true. That's how certain it was in people's mind by the mid-1980s. And then people are convinced by the possibility that this might be right to build the machine, the Large Hadron Collider. $10 billion are spent. They smash stuff together. They're able to jiggle this field in just the right way to flick off a little speck, a Higgs boson, Higgs particle, and the idea is confirmed. That progression, 1964 to 2012, you go from a mathematical idea that nobody believes, everybody thinks is crazy, gets rejected in a journal, to being proven true by experiment. And that's the name of the game. So when we see that happen, that's exactly the pattern that we hope, that we imagine that we are following. Developing mathematical ideas that sound crazy, that seem like they can't possibly be true, until sometime later on, observation shows that they are. So from that perspective, it's a profound moment in the history of these ideas. Thank you very much.